In this video, we'll be going over the binomial theorem. So the binomial theorem allows us to expand terms such as ax plus b when they're to the power of, let's say, whatever number it is, n, and then we can know what the result is. So for example, ax plus b to the power of 3, which will give a certain result. Now the two typical expansions that you don't normally use a binomial theorem for, which you've probably seen previously, are x plus a squared is equal to x squared plus 2ax plus a squared, and x plus a to the 3, x cubed plus 3ax squared plus 3a squared x plus a cubed. Now this is a typical one, so x plus a squared, and it's very important that if you haven't seen this before and you don't know it, that you basically memorize it, as not only do you need to be able to expand it, however you need to go both ways. So you can have to expand it out, but then also there are questions where you see this and you have to be able to factorize it back into this form. So it's very important, as well as x plus a cubed is also important to see, but you're less likely to have to see this and then convert it back, but you definitely have to, in multiple cases, have this and then expand it forward. But with the binomial theorem, it is a lot easier to be able to apply and be able to memorize, as it's just the one formula for all the different cases of n, in which you have this term and you're putting it to the power. So the first thing I want to introduce is Pascal's triangle. If you see here, x plus a squared equals x squared plus 2x plus a squared, and then the other term down here. See that there is a 2 in front of the middle term, and then for x plus a there is a 3 and a 3, and then here effectively are 1s, and here is 1. So why is it that this is 1, 2, 1, and 1, 3, 3, 1? Well, in the binomial theorem, there will be a term to show what coefficient it will be. However, Pascal's triangle is an easy way to see what these terms will be. So you start off with a 1 at the top, and you go 1, 1. So at each level, you're adding an extra digit. So then it becomes 1, 2, 1. And how you get 2 is by adding these two numbers together. So you get this number, and you add them together. And obviously 1 plus 1 is 2. And then the next level is going to be 1. Add 1 plus 2, which is 3. 2 plus 1, which is 3. And then if it's on the side, it's just going to carry over. So it's 1. And then 1, add them together is 4. Add them together is 6. Add them together is 4. And then obviously it's going to be 1 on the end. And you can see that it's symmetrical as well as always. The ends are 1. So 1, 5, 10, 10, 5, 1, and it can keep on going. So here it's for x plus a squared. Here is for x plus a cubed, and you can see the pattern. So these are just for the coefficients. So Pascal's triangle is very useful with regards to this in knowing what the coefficients are. So the actual binomial theorem is this nasty formula here. However, don't look at it too much until you've seen an example, and then it becomes a lot clearer. So we'll go through and say x plus 3 to the power of 3. Oh, that's to be to the power of n. So x plus 3 to the power of 3. So we'll begin by going that n, so 3, 0 times x to the 3 times 3 to the 0. So you can see here that it's x to whatever the power is, and then the second term, so you can think about this as like the first and the second term, and then it's 3 to the power of 0. So we'll say that we'll represent x by the blue and the green, 3 by the green. So you have 3 to the 0 plus x to the 3. Then the next term is 3 to the 1, and then times that by x squared. So we've now decreased this term by 1. So this is sort of represents the n minus 1, or the n minus r when you're going through each of the rotations. So, but because we've taken away 1, you can think about it, we now have to add 1 to the other side. So then we get 3 to the 1. plus this, we then get 3. The next term is plus 3 to the 2, x 1. So we take 1 away, so 2, 1, but now we need to add 1 to the other one. So we get 3 to the 2. Then finally we get 3 to the 3 times x to the 0 times 3 to the 3. So each time we're minusing 1 and we're adding 1 to the second term. So these are all the first terms, which we've been minusing 1 each time. And then the green is the second terms, which we've been adding 1 each time. And then these here, this 3, 0, 3, 1, 3, 2, 3, 3, are the coefficients. And they're represented by 3, 0, which is equal to 3C0, or in general, you have NR, and it represents by NCR. This is a combinatorics, which I'll go through in a bit. But just continuing this example, it looks very messy at the moment. However, I'm not too worried about actually calculating it, but it's just important that you realize the first term to the power of 3 times the next term, the second term, to the power of 0, you're minusing and then increasing. Now, obviously, you can just switch these around. However, you'll get the same answer as you can see in Pascal's triangle. The coefficients are symmetrical, and you're going to have the same, if you switch them around, even though x is going to start off as 0, it will become to the power of 3. If x is at the front, then it'll start off to the power of 3, and then it will eventually get to the power of 0. So you have you have 3 different parts of each term. The coefficients, the first values are x values, and then the second values you can sort of think about as the b values here. You can sort of see how this formula up above makes sense now, because you have these coefficients, which are the same as Pascal's triangle. Then you have a to the x, so the term up here is just referring to, has got an a in it. I was just using x, but you could replace x with ax. And then that's the power of n minus 1, n minus 2, n minus 3, etc. And then b starts at 0, then it's 1, then it's etc. and goes up to n. And you can write this as a sum of. So it's a sum of, you can think about all these different terms. nr, where it's 3, and then your r, which you're increasing, so 0, 1, 2, 3. So this would be where r is equal to 0. So you have ax n minus r. So as r is equal to 0, we have n is equal to 3, and then b r, which r is equal to 0 here. So you don't have to, as I said, you don't need to know the formula as such, but rather than trying to look at the formula and understand it, look at this sort of example. At the moment, just forgetting about what the coefficients are, unless you can remember combinatorics, and then seeing how it goes down, and then it increases. So for the moment, we'll actually solve this expansion, but we use Pascal's triangle rather than the combinatorics to start off with. And we find that the coefficients are 1, 3, 3, 1. So that means we're going to have 1. We're going to times that by x to the 3, by 3 to the 0, plus 3 times x squared, and see how there's always 3 different parts to each term, times 3 to the 1, obviously going 3 to 2, 0 to 1, plus 3 times x to the 1, times 3 to the 2, plus 1 times x to the 0, times 3 to the 3. 3 to the 3. And the x to the 0, 3 to the 0, just equal 1. So that's going to give us x cubed plus 9x squared, because 3 times 3, plus 3 squared, which is 9, times 3, which is 27, plus 27x. And then the final term is going to be plus 27. So we're able to expand x plus 3 to the power of 3. However, we could also move this on to other values of n as well. We just have to add more terms and go from n all the way down to 0. And then with the coefficients, we do have to change them depending on what the n is. So it's important to change the coefficients. Change coefficients. So you have to change the coefficients for differing n values, so power values. So it's important you can't just go 1, 3, 3, 1. However, if it was x plus 3 to the power of 5, the coefficients would change. So instead of using Pascal's triangle, the binomial theorem uses that n0, then n1, n2, etc., all the way to n. Or with the other form, we had nr, where r is equal to 0, and then it goes all the way up to n. Now this is, as I've shown before, combinatorics, where you have NCR. Now NCR is equal to n factorial n minus r factorial r factorial. To give an example, I'll show 5c2. 5c2 is equal to 5 factorial over 5 minus 2 factorial 2 factorial, which is equal to 5 factorial over 2 factorial 3 factorial. Now you can just sub this into the calculator straight away, but if it is tech free, you'll do this by hand. So this is equal to 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. So that's the 3 factorial part, then 2 times 1. Now we can just cancel because it's times, these 3 by 2 by 1 and these 3 by 2 by 1. So we just have 5 times 4 over 2 by 1. And by 1, it just doesn't change anything. So it's 5 by 4 over 2, which will give us 20 over 2, which will equal 10. So therefore, 5c2 is equal to 10. Using the binomial theory with the combinatorics for the previous example, for the 1, 3, 1. So we worked out it was 1, 3, 3, 1. This was x plus a to the power of 3. But if we were using these, we'd have n0, n1, n2, and then n3, where n is equal to 3 for this example with these 4 terms. Now 3c3 is equal to 3 to factorial over 3 factorial 0 factorial. 0 factorial is equal to 1, so that's an important thing to remember. And then 3 factorial over 3 factorial, as 0 factorial is equal to 1, will give us 1. As we can see, that's 1. Then 3c1 will give us 3 factorial over 2 factorial 1 factorial, which will equal 3 by 2 by 1 over 2 by 1. So that's equal to 3 by 2 by 1 over 2 by 1 by 1, which just gives us 3. 3c2 is equal to 3 factorial over 1 factorial 2 factorial, which give us its exact same thing. And then 3c3 is equal to 1, as shown here. Now that should have actually been 0 here. However, if you remember the formula, it doesn't actually change the answer. So 3c0 is the same as 3c3, and that's because 3 minus 0 will just equal 3 here, and then you'll have the 0 term here. And that's the important thing to remember, or an easy way to remember is whenever you have nc0 or ncn, that is just always equal to 1. So looking back at the general formula, it should now make a bit more sense to you.